You are looking at a black hole again. A dark circle, a bright ring, a silent region of space where light itself does not return. It feels like the ultimate dead end. But for decades, physicists and storytellers have asked a tempting question. What if a black hole is not only an ending, but also a beginning? Could it be a portal to somewhere else? To another region of space-time, another part of our universe, or even another universe entirely? To see why this question doesn't come from nowhere, we have to go back to the equations of general relativity. Einstein's theory does more than predict black holes. It also allows for stranger solutions called wormholes. A wormhole is like a tunnel through space-time, a shortcut that connects two distant regions. In the simplest picture, it looks like a pair of mouths with a throat between them. Go in one mouth, come out the other. On paper, you can even connect different universes. The first wormhole solution appeared in the 1930s in work by Einstein and Rosen. They found a way to connect two regions that each look like a black hole through a bridge in the middle. Today, we call it an Einstein-Rosen bridge. It is the mathematically exact solution of the same equations that give us black holes. That is one reason people started to wonder whether a black hole we see in our universe might secretly be connected to something else. But there is a catch. The Einstein-Rosen bridge is not a stable tunnel you can fly through. In the simplest form, it pinches off too quickly. Anything trying to cross would be crushed by the singularity inside before it could emerge anywhere else. So if black holes are portals, they are not easy ones. To go further, we have to ask what kind of wormhole would actually be traversable, and what kind of physics would be needed to hold it open.
Imagine that instead of a dead end, the region near a black hole contained a tunnel.
You fall in through one mouth, travel down a throat, and emerge somewhere else. What conditions would make that possible? In general relativity, space-time curves in response to energy and momentum. Mass and energy usually make space-time curve in a way that attracts. They pull paths together, tighten orbits, and help close off tunnels. A wormhole that stays open and does not instantly collapse needs something more exotic. It needs regions where space-time curves the other way, where gravity effectively repels. In the equations, this looks like matter with negative energy density or pressures arranged in unusual directions. Physicists call this exotic matter. We do not know how to build it in macroscopic amounts. Quantum fields can produce small regions of negative energy for brief times, but so far, nothing we have seen in nature looks like the steady, large-scale exotic matter needed to prop a wormhole open. Even if you had the right stuff, you would face another problem: stability. Small disturbances, like a passing wave of light or a stray particle beam, could make the tunnel pinch shut. The tidal forces near the mouths might be enormous. A ship trying to cross would have to survive not only the journey through curved space-time, but also the risk that the geometry changes halfway through. Some theoretical models have drawn traversable wormholes that obey the equations and remain open. In toy universes with carefully tuned exotic matter, you can write down solutions where signals and even people could, in principle, go through. But these constructions are delicate. They are like bridges made of mathematics, balanced perfectly on assumptions we do not yet know how to realize in nature. So if a black hole were secretly connected to another region by a throat, keeping that throat open would require physics beyond anything we have confirmed. Still, the idea is powerful enough that some cosmologists have gone further. They have asked whether the interior collapse of a black hole might lead not just to a tunnel, but to the birth of an entirely new universe.
When matter collapses to form a black hole, space-time is pushed to an extreme. Inside the horizon, everything falls inward. In classical general relativity, all paths end at a singularity. a place where curvature diverges and the theory breaks. But some researchers have wondered if quantum effects could change that ending. If gravity becomes repulsive at very high densities, or if space-time cannot be compressed beyond a certain limit, the collapse might not go all the way to infinite. Instead, it might bounce. In that picture, the interior of the black hole does not terminate at a simple point. It transitions into a new region where space-time begins to expand again. From the inside, this new region could look like a fresh Big Bang. Space would stretch, matter and radiation would cool and clump, and an entire cosmos could unfold. From our side, we would only see the original black hole. From the other side, its interior might look like the origin event of a separate universe. In some speculative models, our own universe could even be the interior of a black hole formed in a larger parent universe. In that scenario, each black hole inside our cosmos could seed its own baby universe, connected to us only through the horizon we see from the outside. These ideas live at the edge of current theory. They often use simplified models, symmetries, and assumptions about quantum gravity that have not yet been tested. Still, they show how easily the equations of spacetime can be bent into shapes that resemble portals. Whether nature actually builds those portals is another question. To get closer to an answer, we have to ask, if black holes spawn new universes or connect to others, is there any way for us to tell?
If a black hole really opened into another universe, what could we see from here? Probably not very much. Anything that passes through a hypothetical throat and emerges elsewhere would not send signals back to us through normal space. The event horizon would still be a one-way surface for information trying to escape into our universe. From our side, the black hole would look much the same, defined by its mass, its spin, and any electric charge wrapped in darkness, shaping the motion of nearby stars and gas. The interior details, whether there is a singularity, a bounce, a baby universe, or a wormhole throat, could all produce the same exterior signature. This is part of what makes black holes such fascinating puzzles. They hide their most important secrets behind a surface we cannot see past. For now, our best tests come from the outside. We observe how black holes merge and radiate gravitational waves. We map the shadows of supermassive black holes against glowing gas. We search for tiny deviations from what classical relativity predicts. If our theories of quantum gravity are right, subtle fingerprints might appear in those signals. They could hint that horizons are not perfect, that singularities are replaced by something else, or that space-time has more structure than we thought. But a clear, direct confirmation that a black hole is a portal to another universe may be beyond any experiment we can do. Instead, the idea functions as a kind of lighthouse for theory. It pushes us to ask how far we can extend the concepts of space and time, and whether our universe is just one region in a larger, more intricate structure. For now, when you see a black hole, you can think of it in two ways at once. As the ultimate trap, a region from which nothing can return. And as a possible doorway, not because we know what lies beyond, but because our best equations allow more possibilities than our experiments can yet decide. Black holes may or may not be portals to other universes, but they are certainly portals to deeper questions about what reality is